So this video is going to go over ionic compound properties, and more specifically, we're going to go through an example of melting points to kind of discuss the forces between ionic compounds. So ionic compounds are sometimes referred to as salts. So if you hear that expression, whenever you are reading material or anything like that, ionic compounds and salts mean the same thing in chemistry, So some properties of ionic compounds. One is that they are soluble in water. That means they dissolve very nicely in water compared to other compounds. So all ionic compounds will dissolve in water. There are no exceptions to that rule. If the ionic compound when the compound dissolves, it conducts electricity, and that is because you have that freeness with the structure of the ionic compound, which I will talk about here in a second. But it does conduct electricity when dissolved in water, or another way you hear it expressed is that it's molten, or melted. Again, that just allows the electrons to move more freely. When they are in a solid form, they're kind of constricted, and you will see that in a second. So another property of ionic compounds is they have what we call high melting points. So it requires a lot of energy in order to melt the compounds. Again, melting is going from a solid to a liquid. So you need a lot of energy in order for that to take place if it's an ionic compound. Now, why I'm talking about melting points is the fact that ionic compounds are all solids at room temperature. There are no exceptions. So they're not liquids and they're not gases at room temperature. And that will be kind of a distinguishing property between ionics and covalents. And then to kind of tie it all together, these ions arrange in what we call a repeating pattern, or what we call a crystal structure, So because we have positives and negatives, they kind of repeat themselves, positive and then negative, positive and then negative. So I have a little diagram here that I will show you. So here's a picture of a sodium chloride crystal. So what you will see is the sodium ion is probably the one in blue, and then the green one is the chloride. So again, the repeating pattern is the sodium and the chloride over and over and over again, billions upon billions of times. And so that in a solid structure, that positive and negative is kind of linked together. And so that is why in solid form, it does not conduct. But when you dissolve it, the sodium and the chloride then separate, and then you do have conduction. So that's what they mean by repeating pattern, positive, negative, over and over and over again. So to tie this into ionic bonds, we're going to go back to Coulomb's law, which we've talked about previously. So again, Coulomb's law is the attraction between two charged ions. We've been focusing on positive and negatives, but there's other attractions or repulsions that you do have between charged ions, but we're just going to focus on the positive and negative. And we know that there is a factor having to do with distance. So this is a general formula for Coulomb's law. And again, we're going to be focused on the cation attracted to the anion, and then how close they could get together. So remember, your force, if I get an increase in force, that would generally mean my charge has been increased. So that is a direct relationship. If I increase the force having to do with distance, it's actually a inverse relationship. It's an inverse squared, actually, if you remember. So it's an inverse squared relationship between distance, because if I could get two magnets closer together, they will have a stronger force than if the magnets are further apart. So this is our Coulomb's law. Okay, so I now want to apply it to what we call melting points. Okay. So if I have a stronger force between those ions, it's going to require more energy. So that is why it has a higher melting point. So higher melting point means more energy needs to be put in order to what we call separate those ions. Okay, so again, think of that structure. I need to separate those. And so I need to put in more energy if I have a higher force. So what you're going to be asked to do is, with these examples, is to look at their formulas and see which one is going to have the higher melting point between the two. So we're going to compare lithium chloride to magnesium oxide as our first example, and then we're going to look at lithium fluoride versus lithium iodide. Those are going to be the two sets of examples that we work. So the first thing you want to look at is charge. Okay, so the first thing you look at is charge. So what is the charge of lithium? Lithium is a +1. Chlorine is a -1. What is the charge on magnesium? Magnesium is in the second column. It's a +2. Oxygen is right next to the halogens. In that column, it is a -2. So the one with a higher charge, you're going to have a stronger force. Okay, so there's going to be a stronger force between the +2 and the -2 than the +1 and the -1. So if it has a stronger force, I'm going to have a higher melting point. So this is going to have a higher melting point than the lithium chloride based on their charges, Well, do I have a situation like this where I have both of them have the same charges? So lithium fluoride is a +1. Fluoride is a -1, +1, and iodine is a -1. So if you can't compare charges, okay, then you're going to have to compare distances. Now, again, I'm not going to give you any numbers to compare to. So instead, you're going to have to visualize this. So pause the video right now and kind of draw these pictures. So pause the video and draw the pictures. So again, using Bohr's model, lithium fluoride, lithium would have 2 energy levels. So I'm going to draw this circle, and fluoride has 2 energy levels. So I'm going to draw the circles pretty much the same. And I'm not very good at drawing circles. But the little dots in the middle are, of course, your nuclei. And when we're talking about distance here, we're talking between the two ion. What is the distance between those 2 nuclei? So this distance here is going to be different than the lithium iodine. Iodine has 5 energy levels, and I maybe didn't draw this proportionally, but I have 5 energy levels versus 2. So because I have that 5 energy levels, it's going to be a much longer distance here. Okay, so this is a shorter distance between the lithium fluoride versus the lithium iodide. So if it has a shorter distance, so this is a shorter distance, this is going to have a stronger force. If it has a stronger force, okay, so shorter distance, stronger force, therefore that's going to have a higher melting point. So the first thing you look at is charge. Next thing you look at is distance.